Alright, then hitting it again with 5CodingKata, yeah. Divisors of 42 are 1, 2, 3, 6, 7, 14, 21, 42. These divisors squared are 1, 4, 9, 3, 6, 4, 9, 1, 9, 6, 4, 4, 1, 1, 7, 6, 4. The sum of the square divisors is 2500, which is 50 times 50 square. 50 times 50, a square. Given two integers, m and that m is equal or more than 1 and n is equal or more than m, we want to find all integers between m and m whose sum of square divisors is itself a square. 42 is such a number. The result will be an array of arrays or of tuples or a string. Each subarray having two elements. First, the number whose square divisor is a square, and then the sum of the square divisors. So 1 is also valid. The form of the examples may change according to the language. See example tests. There is a note for the Fortran. So let's train. And you got m and n, m and n, and you got between like the certain number. So the first thing will be, so first run the code for all the integers between m and n. 2. Now this is for the specific one, is get all the divisors for integer. Then it is square all the divisors and get their sum. Then we do, what do? We say square all the divisors and get their sum. Then we say check if the sum, if the sum can be square rooted. Append the sum and the solution list, and here is the solution list. And so first run the code for all integers between m and n. So here we say for integer in range, and we say m and n. So we see about that, we just print out integer. Solution list is not defined, that's an empty list. For those concerned, starts with 1. It's 149. Because I always so this we want to between. So we want to oh my god, this is so frustrating. We want to find all of the integers between. So do we find the integers like, so we won't test for 250, we'll only go to 249, and so I guess we shouldn't test for 1, or oh I guess we should. Alright, then we do. Fuck it, okay, fuck you, okay, whatever. So then we do divisor, and we have a list of divisors, and we say for integer in range, for divisor, each integer, we do print divisor, test it out, what's happening. Oh, it takes a bit longer. Oh, it takes quite a while. 100. Oh, so we start at 0. So we want it to start at 1. 1 1 2 1 2. So 1 1. So 1 1 2 1 2 3 1 2 3 4 1 2 3 4 5. Okay, print divisor, and we say if integer modulo divisor equals 0, then we say divisors. Then say divisors append divisor. So that's the first step, get all divisors for the integer, then square all the divisors. So then we say for divisor in, or here we say instead of divisor, we say divisor candidate. Divisor candidate, we say divisor date, and here we say for divisor in divisors, and here we say squared and summed. So at the beginning it's 0, so for all the divisor in divisors we say divisors squared and summed plus equals, and then we say divisor times divisor, divisor times divisor. So here got all the divisors squared and summed, and then we say, and there's sum, so yeah, that's what's happening. If the sum can be square rooted, alright, so here is what we use math. I know this from before, I don't know it's from Kata before, but we say from math import square root, and let's see, like I'll write in Slovenian. All right. Celo število in English, I guess, is an integer. Integer, yes. So we say Python check if number is integer. If a variable is an integer, if integer or decimal, yeah. Check if object is int or float, is instance. Alright. What are we doing? We're doing this, no? We're doing that, no? Digits, no, yes, alright. So then we do, if the sum is square rooted, so we say square root equals to sqrt of divisors squared and summed. Alright, so we say if if is instance square root integer, then we say solution list dot append. What do we want to append? We want to append, okay, so we want to append list. So we say integer and divisors squared and summed, and in the end we just return solution list. Let's see. arg2 must be a type argument 2. Oh, should we just int? Oops, int. Reference before assignment. Line 14. Local variable divisors squared reference before assignment. So I guess that's the you got an empty one. Alright. So here we say print square root. Print all the square roots. Oh, because they are all why is this 1.0? Yeah. Alright, so that doesn't do. Check if float is integer. I float, I int. So that shall always be a float. Check if float is integer. So I say dot is integer. Where is our one? So we use the is integer on float. So it takes square root dot is integer. Test it out. Yeah, now I don't see the solutions. 1 0 2 1 3 1 5 1. So divisor squared and summed. We got a should we call just that. So what's going on? It's 4 3. First, I mean they're correct, but the divisors squared and summed behave a little in a funny way, don't you think? Divisors squared and summed. Let's print the division, and here we do print divisors. Let's see if we get the correct divisors. So at first nothing. Alright, so we shall say print f string for integer. What do we get? 1 2 3 4. So 1 2 is divisible by 1. Alright, so I guess we have to remove this one. Modulo by 0. What if we do 0 over here? Yeah, again. So just remove that. Just say from 1. 1 should be 1, but it's not. Alright. 6, so 5 is just 1, 6 is 1, 2, 3, 1, 2, 4, 1, 2, 3, 4, 5, 6. So this is correct. Let's see, 4, 2. It's 1, 2, 3, 6, 7, 40, 21. 1, 2, 3, 4, 6, 7, 14, 21. 21 and 42 is its divisor. Alright, so we say plus 1. That's a rule that... Oh! Now just everything passes. Okay, so that was the thing. That thing always confuses me. I must admit. That thing always confuses me, plus 1 and minus 1. Yeah, let's make an attempt first, like maybe we missed some of them, you know? This goes... Oh my god, is it gonna time out? It can happen that it times out, you know? Oh, it shall time out, you see? Yeah. Because it is... yeah, that's why we use the optimization, right? That's why we used optimization. So where are the bottlenecks? I guess the bottlenecks are in checking. Yeah. Alright, so the bottlenecks are the problem. So if we don't touch the math behind it, so first we do, for every integer, we first find the divisors, and then we gather them up and we let's see how far are we. Say define list squared, take m and n, to the print m and n. Redefine that a little bit and attempt that. Let's see how many requests we get. Quite many of them. Takes so that is it. Only 50 tests. All right. So then say tests ran is 0, and every time say global test. Oh, or we don't need to do that, we just do tests ran plus equals 1, and in the end we just print out tests ran. Reference before assignment, so it says of global tests ran. So make an attempt. I don't know why it takes so long. 40 random tests. So yes, it's run a specific way. There is some of them. There is quite some of them. So I can't even know how far do we come. Alright, so this is again this optimization. So let's Python find divisors. Find all divisors. So we use oh, we can like yeah, we did that. We can use a bottleneck. For example, quit cd1 and cd, what do we do? Python sandbox. Here we go, touch bottleneck py. We open it in code. So we say chaining of that. Let's just copy. Going to the bottleneck, paste, and then we say list squared from 1 to up to how high does it go? Yeah, those are pretty high numbers, quite some. Ain't that right? Alright, so we use that, and damn it, which thing did we use? So we do Python code profiling, because I can't, like, is there a, yeah, source activate and do pip freeze. So we do Python 3, then we do bottleneck, and we do scale in. That's the tool, scale in. Alright, how do we use it? Scale in, test. Cancel suggestion. Scale in, bottleneck py, ignored. Oh, okay. So that's taking. Oh my God! It's one of those things again. There's one solution that I still have yet to optimize that I'm working on for like 14 days, more than half a month now. And this one is still working. I guess this is a pretty high number. What if we remove yeah, so I guess there is a really high number what we're looking at, so let's just run it again with that lower number. And is that again too much? Well, let's just take a really small number. Program did not run long enough to profile. What about now? Oh, now we did. Yeah, it's the divisor's fault, you know. You see that? See that? Oh, now it's gonna take even like longest before times 10. I just wait for that. Yeah, and also my computer is pretty loud. Wow, it's taking a lot of time. Look. It took half a minute, oh my god. It took half a minute to sort number this big. And the main bottleneck is here. Yeah, it's searching for divisor. So we gotta just find Python fastest way to find divisors. What is the best way to get all the divisors? Here's a very dumb way, yeah, but a smarter algorithm. So this dude tried. Many thanks to Great Hegel and his smart way. Wow, calculating all divisors of that took 0.1 seconds. Wow. Stop saying this is a duplicate of that post. So this is given your factor function, here is a divisor, okay? So we got factors list, factor generator. So we got factor generator. What does the factor generator do? I can find prime factors and their multiplicity fast enough. I've generator that generates factor in this way. Okay. So uses that one, factor generator. Says length of factors, and this f. Well, true yield reduce. Okay. So that is like another challenge. Will I get like a fast? The simplest approach. This is like a generator. A generator is something to try. But I shall just stop now because I want to get to sleep at a specific time, and I'll leave that problem unfinished.